So today we are going to be looking at 3.9 inverse trigonometric functions. So please have your notes open up to 3.9. Inverse trig functions, we've looked at them a little bit at the beginning of last unit, and I kind of just did an overview of some of the trig that we had seen previously. So inverse trig functions, these are our arc, sine, arc, cosine, arc, tangent, or sine inverse, cosine inverse, tan inverse. And these are what we use to allow us to find angles. We did this when we had triangles. So say a triangle, something more here. So say a triangle, we had this angle here. We're told, hey, this is 3, 4. Find the angle. And you said, oh, okay, so that would be tangent of theta equal 3/4. And you said, oh, okay, theta would be tan inverse of 3/4. We use the inverse function to allow us to find the value of unknown angles. Now we're going to be looking at these more as functions today than just finding an unknown angle. That's what we had done previously. But we're going to be looking at them as functions and as the inverses to sine, cosine, and tangent. So one thing just to remember, the reciprocal of a function is not the same as the inverse. Talked a little bit about the reciprocal function. So case in point, sine inverse and cosecant are not the same thing. You see that written here. Cosecant of x equals 1 over sine, whereas the inverse sine inverse of x is equal to arc sine. Now one thing to remind ourselves, arc sine, arc cosine, arc tangent mean exactly the same thing as sine inverse, cosine inverse, tan inverse, and will be used interchangeably a lot. But whenever we see sine to the -1 does not mean actually a -1 power, it means the inverse. Just as when we would have f inverse of x would be the inverse, not the reciprocal. And that can get confusing because when we see something like 2 to the -1, that does mean reciprocal. It means 1/2, 1 over 2 to the first. But whenever we do -1 power to a function, it means inverse and not reciprocal. Who came up with it? I don't know. It does provide a little bit of confusion there. But just want to remember, when you have -1 on a function, it is an inverse, not a reciprocal. Now we can use all the different inverse properties that we have seen before. So a couple things that we talked about when we dealt with inverses is in inverses between f and f inverse. The x and y coordinates are swapped. So case in point, we have 3, -4 is a point on f, then flipped, -4, 3 is a point on f inverse. When graphing f and f inverse, they mirror each other over the line y equals x. And a function has an inverse function if it is 1-to-1. That's very important that I bolded function there. It's an inverse function. Every function has an inverse. But whether or not that inverse ends up being a function depends on whether or not the original one was what we call invertible or 1-to-1. Meaning it has to pass the horizontal and vertical line tests. So let's go ahead and look at sine, cosine, and tangent. Let's start with sine. Does sine pass the vertical line test? If I draw vertical lines, does it go through just once? So it's a function, it's passed the vertical line test. What about the horizontal line test? Does it pass the horizontal line test? No. Since it fails the horizontal line test, this is not invertible. What about cosine? Does cosine pass the horizontal line test? No. Also not invertible. What about tangent? Does tangent pass the horizontal line test? Not invertible as well. So these three functions are not invertible. So the answer to this question here, are cosine, sine, and tangent invertible? And the answer is no. They are not invertible. And we can actually see that even better when we look at what if we were to just switch the x and y and look at their inverse. Well, the inverse of sine, when I switch x and y, notice I wrote that as x equals sine of y, would be this function here. Does this pass the vertical line test? It passes the vertical line test. Sine of y? No, it does not. So this is not a function of x. So therefore, again, sine is not invertible. Because when we look at its inverse, if I was to just completely flip sine across the line y equals x, this is what I would get. And it's not a function. Same thing with cosine. X equals cosine of y. This is what we would get. And x equals tangent of y, we would get this. All three of those are not functions. So back when we looked at things being invertible or not invertible, we said if a function is not invertible, then we need to apply a domain restriction. And that's what we're going to concern ourselves with for the rest of the day, is what are the restrictions put on sine inverse, cosine inverse, and tangent inverse. What are the different domain restrictions or different restrictions? So let's go ahead and start by looking at sine. So if you turn the page, we have some information about the inverse of sine. So on the left, we have the graph of sine, some of it, a little chunk there. And sine, again, would have the little arrows there indicating we're going on forever. And right next to it on the right, we have the graph of arc sine, or sine inverse. What do we notice about this graph? Kind of does look like tangent a little bit. What else do we notice? It has two ending points. I purposely had it graphed and drawn that way with those points nicely bold there, because this does not go past those points. This would not have arrows. If I put arrows here, that would be incorrect. There are no arrows. Those are ending points. It's cut off. Because again, we only are able to take a little chunk of our sine function. And so on the sine function on the left, I indicated what portion of the sine graph we are limiting ourselves to get an inverse function, to make it invertible. It's just that little chunk. And looking at sine, what x values is this chunk going from? What x values? Negative pi over 2 to pi over 2, right? And if I look over at the arc sine function here, I now see that on the y-axis. Why did it change from the x-axis to the y-axis? What do we think? Any thoughts? Why did that negative pi over 2 to pi over 2 change? There were x values changed to y values. What flipped? the x values and y values. Remember, that's a property of sine functions. We reminded ourselves of that right here. X and y coordinates switch. So if we have an x value, it becomes a y value. And that just holds true because these are functions. And we can actually even see it if we take that specific point. This point right here would be the point. So this point would be the point negative pi over 2, comma, negative 1. And if we look at its corresponding point over here, what is the new point on our inverse function? Negative 1, negative. Did the x and y switch? Yes, they did. Because these are inverses. X and y switch places. Okay? Now, if I was to, let's just look at this right here. Between this sine function and this x of y of sine, again, we took just this little chunk here on the sine function that I'm marking out in green to be able to get a invertible piece. So down here, it would actually end up being this little chunk right here. And all of that is a function. If I take just that little piece, and it's as if I'm cutting off the rest of that sine of y graph. Because if I include any more of it, it will not be a function. Now, technically, I could have picked maybe this piece up here or this piece up here. Why we picked the one about the origin, it's probably because we like to put things around the origin. But somebody much wiser than me, I guess, decided upon that would be our inverse portion. So that's what we have. Now, since we are taking our y values or our sine function from negative pi over 2 all the way to pi over 2, and that is it, that provides a restriction for us. And that is that domain restriction right here, that our outputs for sine inverse can only be between negative pi over 2 to pi over 2. Now let's think about that on this circle here. First off, where do we find pi over 2 on our unit circle? Going around the unit circle, where is pi over 2? At where? 0, 1, okay. What's the degree up there? 90 degrees. So up here at the top, right? 0, 1, pi over 2. So that's positive pi over 2. Where do we find negative pi over 2? $270? Yep, down here at the bottom, negative pi over 2. So if I am going from negative pi over 2 to pi over 2, and that is my kind of chunk of the graph that we're looking at, which two quadrants are then involved? If I'm going from negative pi over 2 through 0 over to positive pi over 2. 1 and 4. And it ends up that those are the only two quadrants that we involve when we are looking at sine inverse. Now, if I'm looking just at sine, I do the whole thing. But for sine inverse to be a function like we saw, we have to restrict it from negative pi over 2 to pi over 2, which means I can cross out 2 and 3 quadrants 2 and 3, because it's not part of our range of sine inverse. And that's what I say in the first bullet point here. To be a function, arc sine is only defined in quadrants 1 and 4 of the unit circle. Otherwise, it would fail the vertical line test. Also, the second bullet point says that angles used in quadrant 4 must be read as negative. So let's go ahead and look at a problem to see how that would pan out. Let's look at problem 1a. Arc sine of negative 1/2. Now remember, our inverse trig, our arc sine, allows us to find an angle theta. So this is equal to theta equal to an angle. And often I like, when I'm dealing with inverse, it just helps me see this a little bit better. Sine of what angle is equal to negative 1/2? So where does that happen? When does sine equal negative 1/2? Now, if we can't see that in our head, let's go ahead and pull out our unit circles then. Let's go ahead and grab those real quick, please. We'll need them for the rest of the day. All right, look at your unit circle. Again, we're answering the question. Sine is equal to negative 1/2 at what angle? There are two of them. Remember, which one is sine, the x or the y value on our unit circle? The y. So this, we're looking for a point that has a y value of negative 1/2. So look around on your unit circle. There are two places. Go ahead and identify both of them. All right, so where does that happen? At what two angles in radians? Where does sine equal negative 1/2? What was that? In radians? 7 pi over 6. So that happens at 7 pi over 6. Where else? What was that? 11 pi over 6. So it happens at these two places. However, we had a restriction on sine inverse. Which two quadrants do we use for sine inverse? 1 and 4, because we go from negative pi over 2 all the way around to pi over 2. So I don't want anything from quadrant 2 or 3, so 7 pi over 6 is not the answer I want. It will be 11 pi over 6. However, there is another caveat. What was the second bullet point again? What did it say? The angles in quadrant 4 must be read as. So instead of 11 pi over 6, what would I want? Negative 1 pi over 6. That is a negative 1 pi over 6, and that would be our answer. So again, we want 11 pi over 6, but we can't give our answers 11 pi over 6, and if we give our answers 11 pi over 6, we will be wrong. So instead, we want to make sure we write it as the negative version of the angle, which is actually a negative coterminal angle to 11 pi over 6. And so then that one would have to be negative pi over 6. And again, that's anything that we pull from quadrant 4. All right, with that in mind, I want you to go ahead and look at B. All right, that should be good for this problem. Again, here we are looking for an angle. So sine of what angle is equal to rad 3 over 2? Where does that happen? So again, sine, we can ignore quadrants 2 and 3. So within quadrants 1 and 4, where does that happen? Positive rad 3 over 2. Ellis, so where would that happen? What angle? Pi over what? Pi over 3, good. So if we go up to pi over 3, that would put us at positive rad 3 over 2. A nice thing about doing about quadrant 1 is that that would be our answer, because that's already between negative pi over 2 and positive pi over 2. So our answer would be pi over 3. Again, the other place where sine is equal to rad 3 over 2 is 2 pi over 3, but that's in quadrant 2. And quadrant 2 is beyond our restriction. It's outside, so don't want it. All right, I want you to go ahead and look at problem C, please. Think about that one real quick. All right, I've given you some time to mull over that one. So sine inverse of 2. So again, we're looking for an angle. So when is sine of what angle? When is sine equal to 2? When does that happen? Did you find anything on your unit circle that works? That's problematic. Well, this, if I was to think about this as an equation, this would be sine inverse of x is equal to an output, maybe y. So x2 then is an x value, x equals 2. Let's look back up. Just right above, we have this lovely little box. What does it tell us about our domain? Where are our x values going to have to be? Between -1 and 1. So does 2 fall within that range? No, it does not. So what do you think that means for our problem? I wouldn't say necessarily undefined, because like tangent has that answer of undefined at like pi over 2, right? But I would say no solution, because there is literally no place where sine is going to be equal to 2. That is outside of our range. So because of this, we can say since x equals 2 is not in the -1 is less than or equal to x is less than or equal to 1, then there is no solution. We can also think about this another way, thinking about the sine of theta equal to 2. And that one, if we think about the equation y equals sine of x, and we think about the graph of sine of x, sine starts on the midline, goes down and around like this, right? We did a lot of those sine graphs. What was the maximum value for sine on the parent graph? 1. What was our minimum value? That's another place where we see, hey, sine has to be between 1 and -1. And on this one, if we put that 2, that'd be out here, and that would never have a point on the function of sine, because sine bounces back and forth between -1 and 1 and will never reach 2 unless, of course, I apply some transformations. But this is, we're looking strictly at sine of x, no transformations, the parent function. So it will never reach 2. All right, let's go ahead and turn the page and look at cosine now. I'm going to go ahead, just looking at the time, I'm going to quickly go through the properties of cosine inverse and sine and tangent inverse. Then maybe we'll have a time for one or two problems. So cosine inverse looks similar, but also very different from sine inverse. On this one, whoever is responsible for all this back in ancient days of math and decided upon this stuff, they chose the chunk of the cosine graph going from 0 over to pi to be the chunk of our inverse. So if we look at our inverse again goes from 0 to pi, and we see that inverse behavior, that that x kind of chunk from 0 to pi became a y from 0 to pi. This became y values, and the x values were the y values to begin with. And we see in that graph from -1 to 1, so our inverse goes from -1 to 1 on the x. Now, since I'm going from 0 to pi, we have another restriction. So thinking about cosine inverse here. This is for cosine inverse. Cosine inverse goes from 0 through pi over 2 all the way over to pi. So which two quadrants are involved with cosine inverse? 1 and? So which two do we get to cross out? 3 and 4. Those aren't used in cosine inverse. So this is different from sine. Sine was 1 and 4. Cosine is 1 and 2. Nice thing about doing from 0 to pi is I don't have to worry about any negative angles. I can just read it from the unit circle and be good. Okay. Now, we have similar restrictions on domain and range. The domain restriction is the same as sine inverse, -1 to 1. So again, if we have something similar to that last problem, we're told to find, like, I don't know, cosine inverse of 5, we would be able to say, hey, that has no solution because 5 is not between -1 and 1. Range, however, is different because we're going from 0 to pi instead of -pi/2 to pi/2. But we do have similar restrictions. All right, so that's cosine. Cosine involves quadrants 1 and 2 with that restriction going from 0 to pi. Let's go ahead and take a look at tangent real quick. So go ahead and turn the page again. All right, so tangent takes the part of the function between these two main vertical asymptotes, -pi/2 and pi/2, and creates our arctangent graph, tan inverse. So, interesting thing, tangent has a vertical asymptote at x equals pi/2. What does that become here? What kind of asymptote do we now have? Horizontal. Because, again, within inverse function, what switches? What switches in inverse functions? The x and y. So I had x equals pi/2, but that becomes y equals pi/2, which is a horizontal line. So we get two horizontal asymptotes here. X equals negative, or actually not x equals. I started with x equals, and now I have y equals -pi/2 as a horizontal asymptote, whereas originally I had that vertical asymptote of x equals -pi/2. So we again are seeing that inverse behavior of x and y switching. And also another interesting thing about tangent, because of that asymptotic behavior, tangent actually does not have endpoints. We can put arrows on tangent. It goes on to infinity. So we could actually state the end behavior of tangent, saying the limit as tangent approaches -infinity on x, the tangent function approaches one of these vertical asymptotes. Now, again, we have this restriction between -pi/2 to +pi/2, so let's think about that in terms of quadrants. So again, if I go from -pi/2 all the way around to +pi/2, this is for tan inverse, which two quadrants are then involved? 1 and which do we get to cross out? So what does this look like? Somebody said it looks like sine inverse, right? Yeah, tan inverse and sine inverse actually share the same range restriction. They both go from -pi/2 to +pi/2. And, real quick guys, real quick, just like sine, anything in quadrant 4 must be read as negative. So sine and tangent share those same features.
Also, anything in quadrant 1 is positive.
Correct. And that's true for all three. Now that we've gone over the properties of sine inverse, cosine inverse, and tan inverse, I want to go ahead and finish up with a couple more problems, starting with problem 2, our arc cosine and cosine inverse. So problem A here, we have arc cosine of rad 2 over 2. So this is, again, we're like we did with the sine inverse. This is our theta. So this time we're going to think cosine of what angle is equal to rad 2 over 2. So if we think about our unit circle again, cosine, we're looking in quadrants 1 and 2. 3 and 4 are not used when dealing with cosine inverse. So where does cosine in those two quadrants equal to positive rad 2 over 2? Well, that would occur at pi over 4. So our answer would be pi over 4. Problem B, we have cosine inverse of negative 1/2. That is equal to theta. So cosine of theta equal to negative 1/2 again. In our two quadrants for cosine inverse, where does cosine equal negative 1/2? Well, that would happen here at 2 pi over 3. And since we're going from 0 to pi, we don't have to write that as a negative angle. We can just go ahead and say our angle is 2 pi over 3. All right, let's go ahead and look at a couple tangent examples. So for tangent, we're going to be looking at values of tangent. What can definitely help for this is to go back to our day 1 of 3.8, where we wrote in all the different values of tangent that we have here. And hopefully you went ahead and started adding these to your unit circle, because that will definitely help in this type of problem here. So for this one, problem number 3, problem A, we're looking at arc tangent of rad 3. So this is again asking us tangent of what angle is equal to rad 3. And again, looking for tangent, we're looking at quadrants 1 and 4. And in quadrant 4, we have to be a negative angle. Well, if we go back to our notes from there, we can see right here we have rad 3, and that was at pi over 3. So we can go ahead and safely say our answer is theta equals pi over 3. All right, let's go ahead and look at this one here. So tangent of what angle is equal to negative 1? Again, looking at quadrants 1 and 4. So let's go back here, looking at quadrants 1 and 4. Negative values are down here, and we see negative 1 happening at 7 pi over 4. So let's go ahead and go back to this problem. So we're down here at 7 pi over 4, but like we've said before, we want this measured as a negative angle. So we'd have to say that that is negative pi over 4. So our answer theta would be negative pi over 4. And that would be our answer for that problem. And this thus concludes our video looking at inverse trig functions.